So welcome back to the afternoon session. We're going to start with Bartolomeo. Bartolomeo, please. The floor is yours.
Okay, so thank you very much for the invitation and for also for being here. I'm very excited to talk about some work we've been doing in my group on the analysis of first-order methods. And you may be wondering what graphs of learning have to do with anything about this. So I hope that by the end of the talk, this will be more clear. So just to give you context of where these problems come from, I'll tell you a little bit more about what I do, what we do in my group in general, and then I'll dive more into the topics of today. So in my group, we try to look at problems that range from, for example, logistics, energy, robotics, or transportation, where we need to make decisions in highly dynamic and uncertain environments. So you could imagine seeing problems where you have unforeseen circumstances that appear, for example, a really high demand in an energy system or a failure in one of the actuators of your robot. So if you're, in order to adjust the sequence of decisions that you make in these kind of situations, optimization can offer a very powerful tool. You could just change the optimization problem you're solving in order to compute your decisions and adjust your constraints or your objective in order to take into account these circumstances that change. So this is very powerful, but in order to make it work, we need to first of all be able to solve these optimization problems. And sometimes this may mean that you need to solve them within a few minutes in energy systems or within a few milliseconds in robotics applications. So really being able to guarantee that these algorithms run in real time is very important. And also another thing to take into account is the fact that many of these systems are uncertain, so being able to guarantee that the solutions that we compute satisfy our constraints with high probability is also another part that is crucial in many of these settings. So in my group, we try to combine techniques from the areas of optimization, learning, and control to tackle these two issues, primarily building formulations for which that give us solutions that satisfy operational constraints with high probability under uncertainty, and then optimization algorithms that are guaranteed to return high quality solutions in real time. And the idea is always to connect them to applications, including some of the ones that I mentioned before, from autonomous systems to power systems and healthcare, using data and computations. And I always like to build software tools that try to do that, especially open source ones. So the goal of this talk is to dive more into this part, which is building optimization algorithms that are guaranteed to return solutions in real time and to return solutions that are of high quality. The algorithms that I like to focus on are first-order methods. And the problems that we solve in these applications are, I focus a lot on parametric convex optimization problems. These are problems for which every time we observe something new in our system, for example, it could be the demands in our energy optimal power flow problem, then we need to solve an optimization problem where we want to minimize a convex objective function of our decision z, subject to satisfying convex constraints that are defined by z that lives in a set C of x. So every time x changes, the problem changes, but it's always a convex problem that we're solving over and over again. And to model this, we will assume that x belongs to a distribution of parameters that we encounter. Okay? And the idea is that we want algorithms that perform well for these types for the distribution of interest for a given application. Okay? First-order methods are, for example, algorithms that work like this. Projected gradient descent, we do a gradient step in the part of the objective function that in this case is smooth, and then we project onto the constraints. And if we iterate over and over again with the right step size data, we are guaranteed to converge for these convex problems. And these methods have been around for a long time. I would say they've seen a resurgence recently for two main reasons. So one is that the iterations are cheap in the sense that they can be scaled to very huge problems that can run on supercomputing clusters because they rely on cheap operations. But also on the other end of the spectrum, they can be deployed on very small embedded hardware for edge computing or robotics applications. These are the same algorithms. And in both cases, depending on the application, we need to be able to guarantee that they give you a high enough quality solution in real time. These methods were, I would say, neglected for a long time in favor of other techniques such, for example, like the simplex method for linear programming or interior point methods for nonlinear programming. And the main reason was that these methods were believed to require lots of tuning in order to give a general purpose algorithm that you could deploy. But recently we've seen actually lots of general purpose algorithms that can solve practically relevant problems that are actually general purpose. For example, Google developed this solver PDLP that is based on a primal dual method, primal dual hybrid gradient method, and also NVIDIA recently released an open source version of their implementation for GPUs. I was involved in the development of a quadratic programming solver that was based on similar algorithms, the alternating direction method of multipliers. There's also more recent implementations of generic proximal algorithms for quadratic programming. And I would say if you want to solve even more generic convex problems, you could use methods like the splitting conic solver or SCS and other techniques that have been developed since then. So I would say these solvers are remarkable from the standpoint that they can be considered general purpose. However, if you played with any of these, you know that you can break them. You can always find these instances for which they suffer and they converge more slowly than what you would expect. And this could be an issue if you have an application for which you need a solution within a few number of iterations or within a specific real-time constraints. And also, it's even more of an issue if you have limited computing power and you cannot just parallelize more your computations and increase your computing power. So how can we understand a bit more how these first-order methods work in order to design them and guarantee that they give us solutions of good enough quality? So first-order methods, as I said, have been around for a while. And I would say recently, the way that in many mathematical fields we started thinking about analyzing different objects is through computer-assisted analysis, right? There's people that are way smarter than me that are constantly saying that computers can help us analyze, for example, proofs, formalized proofs, and also they can help us analyze first-order methods. So in my case, I could just go on ChatGPT and ask, how can I do that? And the first thing that it would tell you is that you could use the so-called performance estimation problem, which is one of these frameworks that allow us to study first-order methods and solves an optimization problem to give us guaranteed of the analysis. So who's familiar with this type of work or performance estimation here? Okay, I see maybe 2 hands. So I'll give you maybe a short overview of how that works and how it connects to the problems that we're trying to solve here. So the performance computer-assisted analysis based on the performance estimation problem work like this. So first of all, they don't assume a parametric structure. So you just have, let's say, minimize f of z, which is a convex function. And you have an algorithm T that operates between zk and zk plus 1. So to analyze this algorithm, the performance estimation problem formulates an optimization problem where you maximize a performance metric, which could be the distance to a solution or the fixed point distance between the last 2 iterates. So you can choose the metric. And then the constraints are that you want to optimize over all the functions that live in a function class that you assume. For example, in traditional optimization courses, this could be strongly convex and smooth functions. Okay? And then you want that the iterates are generated by your algorithm T on the function that you're considering right now, f. And then you have an initial condition, which could be, for example, the initial distance between the 2 iterates or the initial distance to optimality. So you can choose your favorite initial condition. So this problem is very nasty because, first of all, you're maximizing a norm, which is non-convex, and also it's a functional. You're optimizing over the space of functions, so it's infinite dimensional. So how do they work out the solution? First of all, you can realize that instead of representing the functions everywhere, you can represent them only at the points of interest, which are the ones that your algorithm encounters. So in this case, you could define interpolation conditions that tell you that are constraints of this problem that guarantee that there exists a function in your function class such that the function value and the gradients are the ones that are encountered by your algorithm. So you can, for example, if you have a convex functions, these conditions are necessary and sufficient and correspond exactly to the first order convexity conditions. But if you have more complicated functions, there's a vast literature on trying to build necessary and sufficient conditions for those classes of functions. Now, this is not the end because we still get a QCQP to solve if we impose interpolation conditions instead of the function class membership. And these interpolation conditions give you quadratic inequalities. You can see that these things that are highlighted in orange are products between variables of your problem. So to deal with that, this literature constructs a gram matrix where G, that is positive semidefinite, which is given by the product of P transpose P, where P is a matrix obtained by stacking along the columns all the iterates and the gradients of the algorithms that you encounter. And also F is the function values that you encounter. So this SDP has very nice properties. I'm just going to mention a few. First of all, it's a tight reformulation. It's not a relaxation. It can give you proofs by looking at the dual of this SDP, and it can be useful also for algorithm design. And there's a beautiful connection between the dual of this problem, and also there's a vast literature on using these methods, and there's many more papers appearing every day, including not only for studying the algorithms, but for algorithm design. So this one, if you haven't heard about it, these are probably the results that give you the tightest possible bounds known nowadays for this type of problems. Now, how do they work in practice? So let's go back to the parametric instances that I was telling you about, and let's construct a set of easy parametric convex problems. So this is a EMNIS data set, which are this set of handwritten letters. And I blurred all of them, and I would like to solve for each one of them a image deblurring problem, which is a nice quadratic program where I have Z, which is the vector representing my deblurred image. This is a vector between 0 and 1 because it's black and white. And also it's you have this 2 norm that every time I observe a blurred image, I want to minimize this least squares distance, where A is a blurring filter, and then my regularization term here. Very classical inverse problem. And then now I'm plotting the behavior of a first order method that applied to solve this problem. This is the number of iterations. This is the convergence criterion on the y-axis. So you can see that the brown line is what the theoretical worst case bound gives me. And then the black line is the average behavior that I record. So I take every instance in this data set. I run these first order methods for a given number of iterations, and then I take the average, and then I plot the black line. And you could see that the average, of course, as expected, is way below the worst case behavior. But how about the 99th quantile, which for all practical purposes, it's basically close to the worst case for this type of problems? It's much closer to the average case, which means that for these type of problems, the bounds are very pessimistic compared to the actual behavior that I'm encountering. Okay? So why is this the case? There are several reasons. The bounds, by the way, the theoretical worst case bounds are tight, so they're not conservative. They're actually tight for the function classes that we are considering. But are we considering all generic convex problems in this case? Actually, no. We're not considering, for example, strongly convex and smooth function. We're considering all the parametric quadratic problems that arise from this image deblurring problem, which means that this is a much restricted class of functions that we want to analyze our methods over. Also, another types of the analysis that is kind of interesting is that this type of analysis tools, they don't run the algorithm at all. You just formulate this problem and you solve it. But if you can run the algorithm for a few instances, maybe this can give you lots of information that you can use to bound or to understand their performance. So how are we going to tackle these two issues is to go back to the fact that we're solving many parametric problems in practice.
Bartolomeo,
Yes.
So if you go back one slide,
This one?
So it means that the PEP is solving, the brown line is used by solving, is obtained by using PEP.
Yes. Yeah.
And means that the PEP is conservative because it's actually solving a more complicated problem than the one that you are really associated with the data. More general.
Two corrections. So the PEP problem is actually it will turn out to be simpler to solve than what we solve. Mm-hmm. So it's an easier problem to solve. But in terms of it's It just considers...
Not complicated, but more general than what you need.
Yes, so the function class is broader,
yes,
the ones that is included, so it's tight for that function class, but we consider a more restrictive one because it's the parametric instances that we see in practice. And this is actually a recurring theme for also your talk and also the other talks today. I think this will be a constant theme, the fact that we have distributions of problem instances that we care about for a given practical application. Other questions? Okay, so let's go back to the, now following this question then, since in practice we actually solve the same problem with varying parameters, for example, in an optimal power flow problem, the layout of the grid doesn't change between one instance and the other. So it makes sense that there's some structure that stays the same and only some parameters, for example, the demands or the wind forecasts change. Or other problems could be problems in robotics where the dynamics of your system don't change, but the state of your dynamical system is the X that varies every time you solve the problem over and over again. So this creates two interesting things. So the one is that there's lots of structure that we can exploit. Okay, for example, the mappings between parameters and solutions. And then another part is that it generates a large amount of data. We can collect lots of information that is about the instances, the trajectory of the iterates, how well we solve the problems. And these two things are the ones that we will exploit today to analyze these schemes. We will not do algorithm design, which is what, I guess, learning to optimize does, which has also been applied extensively in this area. We will look at first the analysis part in this talk. So let me first formalize a little bit more first of the methods, and then also try to connect them with computational graphs. And then I'll go back to mention which kind of analysis or performance guarantees that we try to construct here. So we will analyze first of the methods with operators that map an iterate zk to an iterate zk plus 1. The operator depends on x, which is the parameter that defines the instant that you're solving right now. So the goal is to find, since we're solving convex problems, fixed points of these operators correspond in many practical algorithms to the optimal solutions that we're looking for. For example, let's take an unconstrained problem. So we have no constraints, and I want to solve it with gradient descent. So z is my variable, x is the parameter that now I fix. So the optimality condition is that the gradient as the star is equal to 0. Gradient descent iteration will look like zk minus the step size times the gradient is equal to zk plus 1. The fixed points of this algorithm will be the z stars that are equal to z star minus the step size times the gradient. So you can easily realize that these are exactly the optimality conditions of our problem. And you could do the same for, I would say, any constrained convex problem, also semidefinite programs. You can construct you can relate the fixed point conditions of your algorithm to the optimality condition that we want to solve. So this means that our interesting performance metric to understand if our solutions are of good quality is the fixed point, the norm of the fixed point residual, which is, we will define it as r k of x. X is the instance that I'm considering, k is the number of iterations passed so far, and r is this function that gives me the distance between the last two iterates. Okay? When we find the fixed points, this quantity will be 0. We could also use other metrics, by the way. I'm not saying that this is the best one. You could also look at the distance to a optimal solution. All the things that I'm going to talk about apply also to that case. Okay? So now, instead of looking at generic function classes, we would like to represent exactly these parametric problems. And to do that, we will connect these to computational graphs. And these, compared to the graphs we've seen in these workshops, are actually very, very simple, because these are just these linear graphs that represent our algorithm. So you can imagine that this, given a problem instance, then the optimizer will represent, first of all, a block that gives me the initial iterate. So this could be a warm start mapping, or just 0 if you always cold start the algorithm. And then the operator t applied capital K times. Okay? This is the graph that represents my algorithm, where capital K is exactly the number of iterations that I can afford in a given application. Right? It could be, it's related to how much time I have in my real-time requirements, and also the computing power that I have, and also the dimensions of the problems. But let's say that this is K is given, then I can start thinking about what happens if I change the parameters, what happens to the candidate solution if I change the parameters. And again, just an example, going back to projected gradient descent, the operator t could represent exactly one step of projected gradient descent. So then the question that I'm trying to answer is, if I change the instances that I'm plugging into the optimizer, which guarantees I can give to the candidate solution that appears after this given number of iterations. Okay? So this is some sort of the sensitivity of this method, of this block with respect to the inputs here. So in this talk, I'd like to focus on two types of analysis, given that we focus on the norm of the fixed point residual, which is the norm of the distance between the last two iterates, zk minus 1, where capital K is the budget of iterations that we have available. So there's two types of approaches we could think about. The first one is a worst case one, right? You have a set of instances. I know exactly that the parameters live in a convex set or even a hypercube. And then I would like to compute the maximum of this function here inside the set of instances that I care about in my application. If this value is below a tolerance epsilon, then I'm happy, and I can guarantee that I verify the performance of my first-order method. And this is very closely connected to the topics of neural network verification, which is about, again, changing the inputs to a network and trying to observe the output and try to see that the network behaves in the way that we want. We can also take a probabilistic approach where we consider this distribution of problem instances from a data set, and then we would like to guarantee that the probability that I don't solve the problems, which means that the residual is above the tolerance that I'm happy with, that's less than a probability bound eta that I can tolerate. For example, I can, in some applications, it's okay if I take longer to solve, let's say 1% or 5% of the instances. Okay, so now I'll focus first on the worst case part, and then time permitting, I'll go on to also in the probabilistic part. So the worst case type of analysis, in order to make the problem, at least be able to tackle the problem, we would like to understand how to formulate this problem of analyzing this first-order method. And we will first restrict ourselves to problems that appear a lot in practice, which are parametric convex quadratic programs. So these are problems where I have decision Z that I want to compute, and then I've had a positive semidefinite matrix P, and this means that the problem is convex polyhedral constraints, and the parameter that define every instance appear in the linear part of the objective or the right-hand side of the constraints. By the way, you can also model linear programs in this way where P is equal to 0. This is also completely fine for our approach. And then the idea is that we would like to solve this problem with our favorite first-order methods, which could be also a primal dual algorithm if we want. And then we would like to analyze what's the worst case value of my performance metric over this distribution of instances, where again I would like to compute what happens to the output of this graph, which is the norm of the fixed point residual if I change the inputs within the set of inputs that are allowed. So then the verification problem becomes, in this case, the problem of maximizing over the problem instances, which are, again, this parameter x that appear here, the performance metric, which is the norm of the fixed point residual here. And the constraints, now you could imagine these constraints to be relatively simple sets that I can deal with, but then the complicated parts are how to represent the algorithm steps here, because now I need to, these are equalities, so they can heavily impact the geometry of the problem that I'm trying to solve. And also, I would like to be able to represent algorithms that are generic enough so that they encompass many of the ones that I've talked about before that are used in practice. So now, the interesting thing is that if you look at parametric quadratic programs, the algorithm steps fall into two classes. So the first ones are linear steps that are, by the way, by steps you could think about layers of this computational graph. And then these linear steps are, for example, gradient steps. If you have a gradient and the problem is quadratic, then these steps are linear. You have a matrix n that multiplies zk plus 1, which is equal to a zk plus bx. But you can have also momentum, acceleration, restarts, also proximal operators of quadratic functions. So many of these steps are just linear conditions that become equality constraints over verification problem. You could also have, the interesting ones, however, are piecewise affine steps that appear when we're dealing with more complicated objects. For example, if you're projecting on the non-negative vortant, you can have one-sided projection that correspond exactly to these ReLU functions here, where you clip the negative components of your vector to 0. Okay? So these look like ReLU functions and appear when you're projecting on the non-negative orthant, which is a very common condition. You could also have other steps. For example, if you have the one norm in your objective, the proximal operator of the one norm is a so-called soft thresholding operator. And this operator is given also by this piecewise affine form that is given in this way, okay, which is very common in these types of algorithms. You could also have other types of steps. For example, if you're projecting onto a box, you could have these types of units that I guess in some of these torsion linear algebra libraries are given by these saturated linear units. These are just literally clipping the output inside a box here. But basically, all these steps for parametric linear and parametric quadratic programs fall into these two categories. And if we're able to represent them, then we can represent lots of different algorithms that we can apply in this system. Yes?
It goes a bit beyond your model, but can you use also spectral steps? In the sense, for instance, nuclear norm or thing, easy function if you do the SVD, or is it totally out of reach?
That's a very good question. Actually, we started from this, or we're now thinking about how to extend this to, for example, if you have semidefinite programs, how to analyze them. That's a very good question, though. At the moment, it doesn't, but I think there are ways to represent it. We can talk also offline about them. Anyway, so these steps, for example, if you're solving a non-negative least squares problem where z is your variable and you want to minimize the least squares objective with non-negativity constraints, you could just represent projected gradient descent with a gradient step, which is affine and follows this form, and then a projection onto the non-negative orthant, which again is this simple ReLU step. So if you work with neural network verification, you know that this has strong resemblance with these types of work, and there's a very similar structure for these types of networks as well. And there's lots of work in this area using various techniques to formulate these constraints. But how do we solve this problem in our case? Since in our case, the objective has a very specific meaning, and also the constraints have also more structure than generic neural network layers. So first of all, let's start by saying that the problem is NP hard. So we cannot hope to solve it, at least in general, efficiently. And this is in this paper with my student Vinit. So we worked on two types of ways to tackle this issue of NP hardness. One is semidefinite relaxations, and the other one is exact mixed integer programming formulations. So let me talk a little bit for a few minutes about semidefinite relaxations, and then I'll go back to mixed integer programming formulation. So you could see that here, if I use now as a performance metric the 2 norm squared, then I could represent this by linear steps, for example, the ReLU step, as bilinear constraints. In this case, where I have zk plus 1 greater than 0, which represents this step here, and zk plus 1 greater than zk, which represents this step here, and then a quadratic equality constraints that represent the product here, or the selection of one of the two regions. So if you develop a semidefinite relaxation, you could define positive semidefinite matrices in this way that scale with the dimensions of your problem, and gives you a convex problem that gives you an upper bound to the true bound that we're looking at. Okay, these are very standard techniques. The difference with the semidefinite program that you get in PEP is that this problem depends on iterated dimensions, so it will become very hard to solve very quickly. But at least, for example, I'll give you a very simple case, which is an unconstrained quadratic programming problem where I change only the linear part of the objective. This problem can be written in this way, where gradient descent are just equality constraints. The objective is the 2 norm squared. And let's say that I now take a set of initial points as z, the set of parameters as x. Then it's not hard to notice that if either z is a singleton or x is a singleton, this problem can be solved exactly with a semidefinite program through the S lemma, because you can condense the equality constraints in the objective, and you're maximizing a quadratic function subject to one quadratic constraint. So let's look at how this type of semidefinite programming relaxation, which in this case is exact, works for a simple unconstrained quadratic minimization problem that you may have seen in a class on gradient descent. So these are same quadratic function here. So x is just 0. It's centered at the origin. And then I have 3 different initial sets, z1, z2, and z3, that are these 3 circles that are small here. The light gray lines are the contour lines of my quadratic function. And then the solid circle is all the points at distance 1 from the optimality, which is the initial distance to the solution. So you could see that PEP cannot distinguish starting from either of these 3 sets, because the SDPs that you get are rotation invariant. So it will only coincide the objective in green with the upper bound that we get in the red case. In the other cases, we can show that if you solve this SDP, you get a much lower bound because we're directly incorporating the structure of the algorithm. Again, this is a very simple case, but it gives an idea that by looking at representing exactly what you warm start the method can give you an edge. And in practical application, this is relevant because if you solve many related problems, you don't warm start. You have a specific region where you warm start. It's not from, it takes a lot of information. Another simple example I wanted to mention is the rotated functions. So this is even simpler. I have the same warm start set, just one quadratic function, and then I just have two quadratic functions with the same smallest and largest eigenvalues. So in terms of the analysis of gradient descent, these are completely equivalent. However, depending on where I start in this red region, I just rotate them with two different rotation matrices. So the eigenvalues don't change, but I'm rotating them. And now depending on where I rotate them, I can get wildly different examples. So the green line is still the optimal value that PEP gives you, but then the orange and the blue line are what our SDP gives us for this problem, depending on the rotation. So the rotation cannot be captured with the other standard analysis techniques because the SDP is rotation invariant, while here by directly capturing the problem, we get a larger SDP, but we can capture these types of situations. Now, if you want to see, we have also more examples here. But as I mentioned before, the SDP that you get may be very large. Okay? So now, instead of working with the SDP, we also try to look at another way to tackle the NP-hard problem, but just embracing NP-hardness and looking at mixed integer linear programming formulation, which is a bit of a crazy idea because we're using mixed integer programming to model a continuous optimization algorithm, but it can give you very good insights. So first of all, to use mixed integer programming, we switch from the 2 norm to the infinity norm for 2 reasons. One is that this can be written with mixed integer linear programming techniques, which tend to scale way better than quadratic programs. And also, most solvers terminate with these types of condition. If you have a requirement of some residual vector, the infinity norm is very good because you bound uniformly all the components of the vector within the same constant. So the infinity norm is helpful. And then the only thing to adjust is to reformulate these steps here that are these piecewise affine steps with the mixed integer constraints. So for example, let's go back to the ReLU step we had before. We could use standard techniques to represent it. And the first 2 inequalities are the same as the bilinear, as the quadratic, as the non-convex bilinear constraints, but then the other ones are to linearize the products, where we add new binary variables, 1 per component of Z, to represent this type of switch between these 2 regions here. And now these other gray parts here are the upper and the lower bounds on the continuous variable zk, which are the so-called big M constants. So the tighter you make them, the more effective the relaxations are, as Andrea mentioned a lot in his talk. So these play a big role. And these conditions are very common in neural network verification and other related approaches. However, you know that if you just write the problem in this way, naively, it's never going to scale more than 10 iterations because the problem gets very large and also the number of variables, binary variables, explode. So how did we deal with this issue in order to exploit the structure of this graph here? So the first thing we did is to look at strong formulations. Right? And there are strong formulations in the neural network verification literature. We converted them to this type of problem that we're looking at. So here I'm showing the soft thresholding operator, which is the proximal operator of the 1 norm. And this operator in 2 dimensions, so when the input, for example, is the sum of the first and the second component of Z, can be drawn in 3D in this way. And you can construct strong formulations of this non-convex region by constructing exactly the convex solve by adding appropriate inequalities here. So you can do it and you do get a convex region for which the relaxation gives you the right extreme points. However, since we're working with an NP-hard problem, you know that it's not surprising that you get an exponential number of inequalities to represent these types of region. And by the way, we constructed these regions for all the steps that I mentioned before, which represent pretty much all the practically relevant steps that are used in many applications. Now, instead of using all these exponential number of inequalities, what we ended up doing is to exploit the fact that the separation problem is actually solvable in linear time. And we use this fact to construct cutting planes at the root node of the mixed integer linear program, and we use them to accelerate the solution later on. So we don't generate cutting planes all over the branch amount algorithms, but we use this formulation at the beginning to tighten the relaxation at the root node, which tends to be, in practice, one of the most effective places where to add cutting planes. Now, is this enough? No, because we are not exploiting absolutely the fact that this computational graph represents a first-order method. It's not a neural network. It is a first-order method, and we know exactly how it behaves on a convex problem if you add more and more layers. So how can we use existing theory to strengthen the formulation of this mixed integer linear program? And this is where we go back to the operator theory and also the structure of this graph to tighten the formulation. So first of all, let's look at the performance metric, which is the distance between the last two iterates. But we could do the same with the distance to an optimal solution. So you know that if the algorithm that we're analyzing is, for example, linearly convergent, then operator theory tells us that we can strengthen we can upper bound this quantity by a constant alpha k, which decays geometrically as a constant c times a rate tau to the power of k. We know because the method, for example, if the quadratic program is strongly convex, we have this type of properties for many algorithms. So now, how can we use this inside the mixed integer linear programming formulation to accelerate the solution? So we could combine these ideas with other bounds that we can compute with existing techniques. For example, bound optimization based on tightening, interval propagation. So all these techniques gives me lower bounds on z at the previous iteration and upper bounds on z at the upper iterations, which, if you remember the ReLU function before, these are the big M constant that we want to make as small as possible. So combined with this operator theory bound, we could do a very simple implication from these two that tells us that I already know valid upper and lower bounds on the iterate at zk, which is the lower bound at zk minus 1 minus alpha k, and the upper bound plus alpha k for every component. So then we could use this fact to just solve the verification problem for an increasing number of iterations. This is something you can't do with neural network. Usually you train it and then you analyze it in this way. But here we know exactly how to add layers because these are just steps of our first order methods. So we could just start from compute these bounds and verify the algorithm at k minus 1 iterations, update the bounds, verify the algorithm for k iterations, and move forward, which is something that makes it very easy to use these types of bounds on the last iterates, where you combine knowledge from operator theory with the structure of this problem that we are exactly describing with this mixed integer linear program. Okay, so let me show you a couple of examples of how this works for two classes of problems. One is a sparse coding problem for signal reconstruction. So this is a lasso type objective where I have a noisy signal x, a known dictionary d, and then I would like to reconstruct the noisy signal in a sparse way, and I do it by inducing sparsity with a one norm regularization. Then I get a very simple lasso type objective. And there's many known algorithms to solve these problems. One is the iterative soft thresholding algorithm, which is a proximal gradient method where I do a gradient step in the smooth part of the objective, and I do a proximal step in the non-smooth part, which is the soft thresholding operator I mentioned before. So again, we can represent this with our techniques because I have a linear step and a piecewise affine step here. We could also do momentum versions, so the fast iterative soft thresholding algorithm that adds a momentum step here, which is another affine step that we can directly encode in our method that actually doesn't make our problem more challenging to solve compared to the non-momentum accelerated version. So then how do these compare? So here I have the ISTA on this column, the accelerated version on this column. I have the first row is for strongly convex problems, and the second row is for convex problems. So you could see that the behavior the bounds tend to be better for strongly convex problems, which are the green theory bounds from the performance estimation problem. And then the red lines are the sample maximum that are obtained by literally sampling in this set where set calligraphic X, which is where the parameters live, and then taking the worst case value across these instances. And then the blue line is exactly the solution of our mixed integer linear program. So the interesting thing is that we can reduce significantly the worst case fixed point residual because we're exploiting the structure of this computational graph. And also, we can exactly capture the ripple that appear, for example, in these accelerated momentum inversions. They're very common. It's very common to see these types of ripples, and our mixed integer linear program exactly captures them, which is an interesting behavior. In terms of execution time, we do take longer compared to the semidefinite program. The semidefinite program from PEP is the green line, and our behavior takes longer time. But again, with these techniques, by constructing strong formulations and also combining operator theory, we're able to scale to 40 iterations, at least for these types of problem, which is way beyond the number of layers used in neural network verification in general. Let me give you one more example. This is an optimal control problem, which is a quadratic problem, where I have linear dynamics A, and then I want to optimize over the sequence of states and inputs of this problem. And then the states are constrained into a box, and then the initial state is constrained to be equal to a given value. This is very common in optimal control, and it needs to be solved in real time. Actually, the model that we're using is a real quadcopter linearized model. So you could rewrite this problem in a condensed formulation where your variables correspond only to the sequence of inputs. This is very common in this literature. So you get a quadratic program where the parameters enter in the linear part of the objective and the lower and upper bounds and the constraints. I could solve it with an ADMM splitting the same as the OSQP solver. And the iterations in a simplified form works like this, where I have a projection between L and U, which is a saturated linear unit, which again we can represent. We need to solve a linear system here, where this matrix is positive definite. We can represent linear system solutions inside our mixed integer linear programming formulation because these are just affine steps. So these are completely fine. And then we have another dual variable update, which is another affine step. So we can represent these types of algorithm easily with our form. And just to give an idea, also for this problem, now we chose different values of the step sizes, which are, let's say, rho, which is, the step size rho is a very important parameter to tune in ADMM. Actually, we still don't know exactly how to tune it for practical applications, but this way could be seen as one way to tune it while guaranteeing that the algorithm solves the problem. So these are 3 different step sizes, rho 0.1, 1, and 10. The green line is what the theory tells us from PEP, and then the blue line is the solution of our mixed integer linear program, and the red line is the sample maximum that we compute. So again, the interesting thing is that this exactly quantify the worst case number of iterations. So for a real-time application like this one, is very important to be able to quantify the threshold on the y-axis under which we can guarantee that we solve all the instances of these problems. And also the execution time can be similar to the PEP SDP, at least for this formulation. Now, it's not very important, the solution time, I would say, but the reduction in worst case bound is very significant, because it means that for some problems we can actually trust these algorithms to run in real time. Now let me give you one more idea about this mixed integer linear programming. So how much do the operator theory bounds help us? So we also show this by looking at the fraction of components where these big M conditions get tightened by the operator theory. And for sparse coding, you could see that for strongly convex problems, after 20-25 iterations, the operator theory bounds start to help the mixed integer linear program for most of the components. And also for convex problems, it happens later because the problem converges sublinearly. So the operator theory bounds are slower, but still give you a tightening of this, of the components of the variables, which is helpful to solve the mixed integer linear program. Similar thing happens for the optimal control problem, actually much earlier, within 10 iterations. So again, if you have a strongly convex problem, the largest benefits in terms of bound tightening based on operator theory are visible in these cases. Okay, so it's important, again, to use as much as possible for known results about this algorithm in order to accelerate the solution of the mixed integer linear program. Okay, so these are the worst case type of analysis. So we looked at how to formulate this problem exactly for this class of parametric problems, and how to use a computational graph structure to understand the worst case behavior. And we used semi-definite programming relaxations and mixed integer programming exact formulations. So now let me spend the last few minutes on looking at probabilistic type of analysis, which is more using data and using the fact that we can actually run these methods on a few instances. So can we use that information to improve the way that we understand these bounds? And to dive into the probabilistic analysis, we can realize that this is strictly connected to statistical learning in some sense. Because the probability of failure of my method, where the residual function is greater than epsilon, which we want to bound to be less than or equal than a tolerance eta, then this is equal to the expectation over the parameters of an error function, which is a 0-1 error function that tells us whether or not we solved that instance. Okay? So this is a loss that is very similar to the losses that we use in statistical learning. So we could draw a parallel between the two. So for classification, we get an image, which is an image of a cat. This is actually my cat. And then in optimization, you take a problem instance that has a parameter x. And then the question you could ask is make an hypothesis. So you hypothesize that it's a cat, or you hypothesize that a value of the residual after k iterations. And then the question is to understand the error, 0 if it's a cat or 1 if it's wrong. And then the error is literally, have I solved that instance up to that tolerance or not? So then we could, the questions in statistical learning is to try to build guarantees on the guaranteed loss for unseen new data, which are new images. And for us, it's for new problem instances coming from the same distribution of instances that are appearing in my application. Okay? So if we start using that, then we can build guarantees by observing a data set of instances and how my method works on a data set of instances. So, and I'm now going to talk about a very simple type of guarantees that we get without learning. Actually, somebody gives me an algorithm and I would like to guarantee with high probability how well it does on a distribution of instances. So what can we do? Very simple. We run k steps, which are the budget that we have, on every instance in my training data set or in my given data set. So I get every instance, I get the candidate solutions decay, and then I compute the empirical risk, which is literally the fractions of problems that I fail to solve within k iterations and a tolerance epsilon. And then the next step is to bound the true value of my loss, which is the expectation over the distribution of problems. Okay? There's many, many, many ways to do it. I'm just going to mention one type of bounds that we could use, which is a bound, sample convergence bound, which is from Langford from 25 years ago. And this states the following, but what I find interesting is that it's very powerful for also optimization algorithms. So this bound tells you that with probability 1 minus delta, which is a confidence 1 minus delta, then the probability of failure, which is equal to our true risk, is bounded by what's on the right side here. So what's on the right side here is a typical bound, a sample convergence bound, where I have the empirical risk here, a regularizer that depends on the confidence that I have logarithmically and the number of samples at the denominator, and then I have the inverse of the KL divergence between these two Bernoulli distributions, which are the empirical risk and the true and the sampled risk. So this is a very common bound. And what does this mean if we compute it and obtain a value? So this tells you, the interpretation is that if the bound is equal to a constant b, it tells you that with probability 1 minus delta, then the fixed point residual, which is our performance metric, is above epsilon after k steps, b fraction of times. Okay? Which it's a very important thing to know if you're somebody who wants to deploy this method in a real-time application. You want to understand what's the fraction of times after which we get the value of the fixed point residual above this threshold epsilon. So let's go back now for the very end, to the image deep learning example I mentioned at the beginning, where there was a gap between the theoretical known bounds and the actual behavior. And let's say that now I have a data set of problems and I run my first order methods in parallel. You could do this in your favorite way, even on GPUs. We do have GPUs implementation of, in this case, the SQP solver, where you can just parallelize these runs for many instances in our training data set. And then I want to plot the fraction of problems that I solve within a certain accuracy. So you could see that I can get different plots like this. So this is for accuracy 0.1, 0.01, and 0.001. And the y-axis is the fraction of problems solved, and the x-axis is the number of iterations. So you could see that the brown line is the theoretical worst-case bound that tell you that I solve no problem, and then after something, a very high number of iterations, in this case more than 10,000, I can ensure that I solve all the problems because it's a worst-case type of bound. And then if the accuracy becomes, epsilon becomes smaller, you need more iterations until you get, I guess the theory tells you that you need around 100,000 iterations to solve this problem. Now the black line is the true fractional problems that we managed to solve in auto-sample. And you could see that it's much less pessimistic, and within, let's say, a few tens of iterations, you get low accuracy, and probably around 1,000 iterations, you can solve all the problems. Now, our bounds are the other line. So the red line tells you the bound after 10 samples. Admittedly, 10 samples are 10 problems for which I run this method, so it's not that much, but it already gives you something a little bit better than the brown line. And then if I run 100 samples, I actually get a line that is pretty good, I would say. So it's not that many instances that you need to guarantee that you, to build bounds on the true behavior of these schemes. And then the green line is what happens if I solve 1,000 of these image deblurring instances and I compute the bound from the previous slide. So this is pretty closely tracking the true empirical behavior, but we can guarantee with high probability that this is the true thing that happens for this algorithm on this distribution of problems. Okay? Which is what tells me that by observing the a posteriori information after running the algorithm, we can build statistical bound that can guarantee that we can solve these problems with a limited number of iterations, much smaller than what the worst case analysis tells us. And these are the red lines that tell you the number of iterations required, so you can see that they can be significantly smaller than the worst case ones. Okay, so let me just wrap up here. So I would like to acknowledge people who were pushing for this work and did I would say without which you wouldn't have been able to have it. So the first one is Vinit, who worked a lot on this performance verification for both semidefinite and mixed integer linear programming formulation. My postdoc Ji-Zoom Park has been involved a lot in the theory behind these schemes and also how to extend this to other types of first-order methods. My student Rajiv who's now a postdoc at UPenn, has been working on the statistical learning side of things. And also Andrea, who has been involved in the mixed integer linear programming part, and also Stefano, who also has been involved in the mixed integer linear programming part. So let me just mention the papers. So the latest one is the one about exact verification with mixed integer linear programming. It's on arXiv. This is the code for all of them. The SDP one is on math programming, and the one about statistical guarantees, where we also do learning to optimize. I didn't have the time to talk about it. Is going to appear on JMLR soon. So let me just conclude. So I talked about several ways to analyze the performance of first-order methods and try to do it exactly for parametric convex optimization. So the first thing I'd like you to remember is that there's a close connection between first-order methods when you have a limited computational budget and computational graphs. And this can help us, and I believe there's way more techniques that we could use to understand the behavior of this fixed length simple graph when we change the input. So I believe there's more synergies that we should explore, especially also in terms of representing these problems. For example, as you've seen this morning with graph neural networks, this is not something that we've been using here. There's also the fact that the parametric structure of these problems matters in practical applications. We don't want to ignore that when we analyze these schemes, the structure really affects the performance if we're constrained to a specific set of instances. The a posteriori information helps. What is a posteriori information is what we can observe by running the method on a few instances. So I believe that to get a tighter analysis, it's important to observe these schemes for some samples and combine more worst-case approaches with data-driven approaches. And on the long term, I believe that this can be used to design new algorithms. I showed you a little bit what happens if we change the step size in ADMM in one of the schemes, but there's way more that we could do to switch from a traditional view of solvers that are one-size-fits-all general purpose solver to solve any linear program or any quadratic program, which if you care about a practical application, maybe you care about only the linear programs that come from your distribution, to another view where first-order methods are task-specific, and you can tune them and train them and guarantee their performance on a specific distribution of instances in order to deploy them on all sorts of computational platforms after you guarantee that you don't need many iterations to run them. And this is, I believe that in the future we will see more of these first-order methods developed and deployed in a similar way as we do with machine learning predictors, where there's a hard work offline, and then online we can deploy them and guarantee that they work well. And I'm not saying we should replace everything with learning, but only a few of the parameters and still maintain the same graph structure. Thank you very much, and I'd be happy to answer any questions. Yes?
One question is, with the tools you are providing, basically you rebuild difficult instances. And there is this belief that in the worst case analysis, basically the instance that you use, at least to make the classic proofs, are very different from the real one. So is it also what you observed there? And with the probabilistic method, I would expect to have instances that are much closer than the worst case. So do you see a big difference into the instances that are rebuilt by the worst case and the probabilistic case?
That's a very good question. So for the probabilistic case, it depends. For example, maybe I'm gonna just switch back to that slide. So I had the slide, the very first one to motivate. So for example, here, so this one here, in this case, it's actually not so far, right? Because the average case is very close to the worst case. And these are just coming from these images here. But again, it depends on many things that we haven't been able to analyze now explicitly. So it depends, I think, on the distribution of parameters, how the parameters enter the problem and affect the optimal solution. So I would say it depends on a few things, but I believe in practice, maybe if you want to get a high probability bound, it could be much closer to the expected value, at least from a very purely empirical observation. For realistic problems, much closer to the average than the worst case. But again, this is something that we haven't explored explicitly besides looking at these problems. But at least with the parametric formulation, we can guarantee that the worst case instance that we find is between the ones that we actually solve, which is, if you look at more generic function classes, it may not be the case.
Could you maybe try to be a little bit more specific where you potentially see applications of graph learning in this line of research?
So first of all, the way that we formulated the graph to represent the optimization algorithms, it doesn't have all these nice properties about, for example, these problems are effectively, for these first order methods, I believe they're you can permute rows and columns of your problem, and in terms of a first order method like this, not branch and bound, but a first order method like this, it shouldn't change, right? While the architecture that we have, it's pretty much dependent on the order of how you represent this problem. So I believe they're representing basically these problems with a graph. For example, this bipartite graphic we're talking about this morning could be very beneficial. Not only for this, also to build bounds to, let's say, generalize the bounds that I built for a specific dimension to higher dimension. This is something that, again, are very specific to a given dimension. And another thing about the graph learning is that I haven't talked at all about learning parts of these algorithms, even though in one of the papers that I mentioned, we do learning. And for those, when we do learning, we can tune things like the step sizes or the restarts parameters or the warm starts. So we have papers on those, but we're not representing the problems using graphs, which I think will limit us in terms of generalizing to different dimensions or even permuting constraints or variables. So I think there's connection that we haven't explored, which I think could be highly beneficial also for first order methods, not only for branch and bound or combinatorial algorithms.
Thanks a lot.
Welcome.
I guess we go into coffee break. Thank you again.